So there was a sudden interruption in the previous session, so I couldn't complete my statement. So this is the actually the problem with the trial version of the Zoom. Anyways, what I was telling you was that suppose we have the following. I'm again taking the pain of writing the thing so that I can at least tell you that what I was trying to say to you. Okay, so these are the only left cosets. These are the only left cosets of this quotient group. Now, whenever you use the Kelly table is actually used to design the composition, outcome of the compositions from the quotient from any finite group. Quotient group 3z 12z by 3z by slash 12z is actually a finite group. You can see because there are left cosets. These cosets are actually sets. So these sets are actually members. So actually now these members are actually infinite by themselves. Okay, in these elements, infinitely many elements are there, but those elements inside the members, they are not constituting the members of the quotient group. Quotient group has this many elements only. So the quotient group is finite. Not there. I'm not talking about 12z and 3z. Remember. So don't get confused. Now, the composition making of this composition is very simple. You have to remember that a plus h and star b plus h gives you a plus b star h. Now, if I use it, then with the help of this composition, I can write it as 0 plus 0 to plus 12h. Now, here star will not be there. Sorry, not star will be star will not be there because the composition is like this. So it will be like this, isn't it? So 0 plus 0 plus 12z. So it will be 0 plus 12z. 0 plus 1 plus 12z. 1 plus 12z. In this manner, there will be no problem in the first row. But whenever you come to the second row, and you try to write 1 plus 11 plus 12z, then that actually becomes 12 plus 12z. 1 plus 12z plus 11 plus 12z actually becomes 12 plus 12z, but there is no such elements like 12 plus 12z. Why? Because R range, the range of R is from 0 to, is from 0 to 12, where 12 is exclusive. Okay, so a cycle will be formed, and that will become exactly equal to 0 plus 12z. So here 0 plus 12z will come. Here 0 plus 12z will come. In the next phase, you can guess that 0 plus 12z will come over here, and this will be 1 plus 12z. In the next phase, 0 plus 12z will come over here, and this will be 1 plus 12z, and this will be 2 plus 12z. In this manner, it will go on. So you try to fill up this particular table, and that will give you the quotient group. In the similar line, I can also give you another problem to practice by yourself. This problem, which is actually similar. You are to prove that 4z is the normal subgroup of z. Z is the set of integers, plus is the operation that we are considering over here, and form the Kelly table of z slash 4z. This type of problems you are actually going to get in the examination. Now again, the same question probably you are coming to your mind, that what sort of questions can be asked from here, because it is this is a very simple question. You may be asked that whether 4z can be considered to be the normal subgroup of z or not. It's a very simple question, but if I want to make the thing complicated, then what I can ask you that you can easily say now, if you by doing this mental calculation, you can easily say to me that there will be 4 elements in this particular quotient group. One element, you can easily calculate it in your mind. One element will be 0 plus 4z, another element will be 1 plus 4z, another element will be 2 plus 4z, another element will be 3 plus 4z. Probably you have already guessed. Now, whenever we are forming the Kelly table, it will be a 4 by 4 matrix type of thing. The order of the table will be 4 by 4. They can ask you the question what will be the element that will come in the third row and third column? Which of the following elements will come in third row and third column of the Kelly table for the quotient group Z by 4Z? So right now, I think that you have already got your trick. You can easily deal with the problem. But suppose, consider the situation of the student who doesn't know anything about this particular, he has not practiced this type of problem. This particular question will be a kind of Hebrew to him. He will not understand what they are asking for. So this is the thing which I wanted to tell you. It's another important problem. Next problem is also very important. The result is actually very important rather than the problem's proof. Okay, so let G be a group. Show that if capital G, ZG is cyclic, then G is abelian. If capital G is by ZG is cyclic, then G is abelian. Now, actually remember, students, that what we study the group theory. Group theory is studied because of 2 things that I can mention to you. First of all, various reasons are there. First of all, your ultimate goal is to get into the section of Boolean algebra. So these are the things, the things that you are studying. Actually, this is polishing your base to get into that part. Boolean algebra, you know very well that it is actually used for circuit building. So whenever you are trying to do some kind of embedding on the chip with respect to the circuit, what will be the path of the circuit, which particular things will commute with one another, how to design that thing, that algorithm, when you are going to apply this type of knowledge, is actually very required. Okay, so that's why this abstract algebra is actually studied. Tremendous other applications are there. If I try to show you all the applications one after another in this particular class, and I'll not be able to complete the syllabus, but I have to mention one such application which is very important with respect to abstract algebra, is the study of symmetry. The study of symmetry in nature. Different companies you have probably seen, they build logos. Okay, so TCS is a kind of logo, then the Amazon has a kind of logo, and various companies, and most of the cases that logo is kind of a symmetric nature, symmetric quality. Some sort of symmetry is there in that logo. Not TCS. In TCS logo, there is no kind of symmetry. I'm just saying that I'm actually trying to say to you. But there are some logos which are symmetric in nature. So how do they form those logos? Do they whether they just do that, or do they apply any sort of symmetric property into it? They put any sort of symmetric property into it. The answer is the yes, second one. They just do not do it arbitrarily. Some mathematical logic they apply, and this is called the study of symmetry. For this, in this respect, I will suggest you go for the book by Gallian. It is called Contemporary Abstract Algebra. Contemporary Abstract Algebra, the book by Gallian. If you just read the introductory section of this book. Okay, this book is available in Library Genesis. If you just read the introductory section of the book, you will get to see what I'm trying to say. Okay, Gallian, Joseph Gallian. If you do not find the book, you ask me, then I have the PDF file with me, I can send it to you. Now I'm going to show that this result, I'm going to prove this result. For simplicity, let us, I shall write ZG as Z, because never try to write ZG as Z, because sometimes you may think that this Z is the set of integers, but it is not. So this type of notations, I actually do not prefer. I do not actually prefer. So I shall consider throughout the problem, I will consider ZG to be Z only, to be ZG. So since capital G is a group and ZG is center of the group, then the group formed by G/ZG will be of the form this, isn't it? Because all the members of ZG, this is the form of the left coset, because the elements of what was the definition of left coset? Let me write. It is this one. This is the definition of left coset. So we can write it as in place of ZG, because ZG is the subgroup of the group. So in place of H we have ZG. In place of A we have considered small small g, and we are writing it as then in that case we can consider this to be in this manner, that G into Z1, where Z1 belonging to ZG. This is the thing. So easily we can consider this to be an element, a set generated like this. So therefore I am writing here that this quotient group G/ZG is actually of this form. Okay, and this will happen for some small g belonging to capital G. Let A comma B belonging to capital G, then AZG and BZG belongs to G by ZG, isn't it? Because whenever I consider the quotient group G by H, its elements are AH and BH. We write it in this manner. So in place of H we have ZG. Remember this. So if I choose two elements AB, we are choosing two elements from A and B, then the left coset AZG and BZG will belong to this quotient group. Now since this quotient group is being generated by G of this type of element, the quotient group is being generated by this type of elements. Okay, so we can write AZG, we can write this set as G to the power n into ZG, and BZG can be written as G to the power m into ZG for some n m belong to ZG, isn't it? Because it is being generated by small gz it is being generated by the element of the following form, of this form. So by definition of the generator, we can get some element from, not from ZG, sorry, it's mistake, some element from this n and m are integers. So the element will be from the set of integers. Sorry, set of integers. In this type of problems, you have to take care of these notations very fine way. Otherwise, you may be, after some time, you may be lost somewhere. You can never escape. So anyways, just check whether everything is all right or not. If you have any type of, if you are observing that I have done any sort of mistakes in writing, then you can point it out. So this is the thing. So far we have written. Now what? Now A belongs to g to the power n. A belongs to g to the power n z g, and no, if this happens, I mean, whenever I can write this element as this and this element as this, then we can say that A belongs to the set g to the power n zg, and B belongs to the set g to the power m z. Okay, and hence again A can be written as g to the power n d, and B can be written as g to the power m h for some d h belonging to z. I'm doing nothing, no trick is being done. I'm just using the definition. Do not think that I'm actually doing any kind of trick over here. If this happens, then these two results automatically imply that they will belong to this kind of left coset. This element will belong to that kind of left coset. And if it is so, then we can express our elements A and B in the following manner, where we are choosing D and H from the center of the group. Now, just take a snapshot. I'm going to the next page. Now, let us start with AB. Now, according to our choice, A is expressed as this and B is expressed as that. Okay. Now, we can recombine the thing together in this manner. Why? Because these things are integers, and you know that these integers are actually commutative with respect to multiplication. So we can commute this in this manner, and this can be written as g to the power n plus m dh. This again can be written as g to the power n plus m hd. This can be written as g to the power m plus n hd. This can be written as g to the power m g to the power n hd, and then again this can be written as g to the power m h and g to the power n d, and this becomes BA, which shows capital G is abelian, which proves the result. Capital G is abelian. So we started with G is a group, G by ZG. ZG is the subgroup, and not only a subgroup, you can also prove this result. I haven't mentioned. ZG is normal subgroup. ZG is normal subgroup of capital G. This simple result I have skipped. Try to prove it. Center of the group is the normal subgroup of G. Proof is simple. If it is a normal subgroup, then we can only construct the quotient group. Okay. If this quotient group is cyclic, if this is cyclic, all the things that we have covered over here, this thing, all these things that I have written, it is happening because the group is cyclic. Otherwise, we will not be able to write the thing. If it is cyclic, then the original group is abelian. If this is cyclic, then original group is abelian. Now, probably you are thinking that what sort of result is this? Now, try to look at it. Just a few minutes ago, in the previous session, we actually formed groups like this, 3z by 12z, isn't it? I also asked you to form a group like this. I also asked you to form a group like z by 4z. You have done this sort of problem, and you have come across the fact that this quotient group contains, depending upon the choice of R, it has finitely many elements, okay, in these quotient groups. So therefore, what, after a certain point, the elements of the group are actually repeating itself. So this group is a cyclic group. This group is the cyclic group. And what is 3z and z? They are abelian. We already know the fact, but suppose this fact is not known to me. Suppose I'm not dealing with the set of integers. I'm dealing with any arbitrary z. Okay, any arbitrary g. Then we can say something about the group G. I'm just saying that, I'm just showing you that the result which we have proved, that kind of relationship with our previous problems. Now, I'm giving you a homework in this case in similar line, just like the way I have done it. You try to do this problem. Try to think about its logic, that let G be a group. Let H be a subgroup of G such that H is a subset of the center of the group. Show that G, if G by H is cyclic, then G is equal to ZG, that is G is abelian. Okay, try to do this particular problem. I think this particular problem is actually very important. So try to solve this particular problem. Hope you are feeling well after all this kind of mathematics that are being done in this particular class. I know it's actually this type of maths is actually very a troublemaker for you, because you have never thought like that. So there are 100 problems on this normal subgroup and quotient group and cyclic and this commutativity. 100 other problems are there. So if I stick to this type of problems, then I'll not be able to further. I'll not be able to proceed further, because many more topics are left untouched. So let me, before I conclude my today's session, let me introduce another important fact, and this is as follows. So I'm going to give you a new definition. At this point, I'm actually dealing with two different structures. One structure is G star, and another structure is G1 star 1. These two structures be two groups with respect to two different operations and two different sets. Suppose we have this. And suppose f be a function, suppose f be a function from one group into the another group. We have dealt with function earlier. We have tried to design a function from a set to another set. At this time, I am not designing a function from a set to the set. I'm actually designing a function from a group to the group. This sort of function, f, is called a homomorphism of capital G into G1 if for all A comma B belonging to G, f of A star B is equal to FA star 1 FB. FA star 1 FB. If this holds, then we call this particular function f to be a homomorphism. I'm going to show you an example. Suppose I'm choosing two groups. Capital G is R plus. R is the set of real numbers. R is the set of real numbers. Okay, plus is the ordinary operation of addition. And G1 I'm selecting to be R plus, set of all positive rationals, positive real numbers. Here I'm only considering positive, not non-negative. With respect to the multiplication operation, you can easily show that these two are groups. Now I'm defining a function. Now I'm defining a function h from R to R plus. Okay, by HA is equal to e to the power A for all A belonging to R. Not every function will be homomorphism. Some special functions will be homomorphism if they satisfy the following rule. So I'm defining the function in the following manner. Now it is easy to observe that if I consider A plus B and if we operate H on that, here we actually used A star B, but yes, here the operation is not star. This operation in the group G is the operation star, and this operation in the group G1 is star 1. When I am taking two elements from G, I'm actually taking their composition as A star B. But when I'm operating the product which I obtain after composing the two elements, if I operate F, the outcome which we actually get will be composed with respect to the operation star 1, not with respect to the operation star. So HA plus B, by definition of H, it can be written as e to the power A plus B. Now e to the power A plus B can be written as e to the power A into e to the power B. And you know that this is HA and this is HP. Just see, here plus operation is there, here multiplication dot operation is there. Here star is there, here star 1 is there, which is true for all A, B belonging to R. Therefore, H is a homomorphism. H is a homomorphism. Next, I am going to discuss, this is suppose example 1. Suppose this is example 1. Example 2, I'm going to select another group, say for example, G, which is Z. Z is the set of integers. The set of integers. Okay. Do not think it I'm considering the center of the group. Z plus with respect to the plus of addition operation. And I'm considering G1 to be the group which is I'm considering the set 1 and -1 and the composition dot. You can easily check this is finite group. It's a very beautiful group it is. Here all the properties of group will be satisfied. It is associative, it is closed, identity is there, which is 1, inverse is there, everything is present. You can check it by yourself. So I'm considering this to be the G1. Multiplication dot is taken and define the function from Z to this. Okay, by the definition is important. How do I define it? Fn equals to 1 if n is even integer and -1 if n is odd integer. This is the way the thing has been defined. Just quickly take the screenshot. So I'm going to check the property and I'm going to check whether in this respect whether I can call this F to be the homomorphism or not. So let Nm belonging to capital Z, if Nm are both even numbers, then from our school days we know that n plus m is even. If n plus m is even, then f of n plus m is equal to 1 by definition, which is written as 1 into 1, which is fn and fm, no problem. Okay. Suppose you can write this as case 1. This is suppose case 1. Now I am doing case 2. Suppose n is even and m is odd, then n plus m is odd. Then by definition fn is equal to 1, fm is equal to -1, and f of n plus m, since it is odd, this is equal to -1, which is 1 into -1, which is fn into fm. Similar is the situation. Similar is the situation when we take the opposite, that is when m is even and n is odd. Okay, now this is my case 3 I am considering. Suppose I am choosing both n and m are odd. Both even has already been done. Even and odd has been done. Now I'm choosing both are odd. Then n plus m is even. Sum of two odd numbers is an even number. Whence means where, while f of n plus m is equal to 1, which is -1 into -1, dot is there, which is fn dot fm. So combining all three cases, 1, 2, and 3, combining all three cases 1, 2, and 3, we find that for any two integers n m, f of n plus m equal to fn dot fm, and hence f is homomorphism from the group Z plus to the group this. So this is the problem. This completes your problem. This completes your problem. Now I can give you a homework. It's a homework. You can take your G to be GL to R. GL to R definition is already been discussed with you. And okay, what is that I'm writing? 2 by 2 non-singular matrices. Set of 2 by 2 non-singular matrices under matrix multiplication. Under matrix multiplication is a group. Just check the book. Okay, and I am considering G1 to be R star. R star, set of all non-zero real numbers under usual multiplication. Under usual multiplication, define f from GL to R star by f of A, capital A is matrix, 2 by 2 matrix, and on the right hand side I am writing determinant of A. Determinant of A. Is f a homomorphism? If f a homomorphism, this is one question. Try to do this. Another example I'm giving you, which you can do as homework. Suppose I'm considering G to be Z plus. Z is the set of integers. G1 to be Z plus. Same thing. Define f from Z to Z by f of n is equal to n plus 1. Is f a homomorphism? This is another problem. Try to do it. Okay, so these two problems I'm giving you. So try to do it and try to find out what is the solution. So and time is also running out. I'm going to stop at this moment here. So tomorrow I'm going to continue further on this particular discussion, and we have to move a little bit faster because before the CA3 examination begins, as many sections of group theory as I can should be finished by then. Okay, so hope you will cooperate with me. If you have any doubts, any problem, you can write in the WhatsApp group. So till then, bye. Hope you have enjoyed. See you next week.